Yeah, hello everybody. My name is Georgy Kucherin, and I am working at Kaspersky's Global Research and Analysis team. Overall, I've been in the cybersecurity community for 2 years. That's not a lot, but as a person who has been dealing with complex malware and APTs every day for more than 2 years, I perfectly know that threat actors do not like it when we, researchers, discover their samples, analyze them, make reports about them, and then discuss them at cybersecurity conferences like now at Virus Bulletin, or discuss them on Twitter. For that reason, malware developers are trying to place obstacles along our path, thus attempting to prevent us from getting deep into the malware secrets. And code obfuscation is an example of such an obstacle. By introducing obfuscation, they make code more difficult to read, and they extend reverse engineering time by days, weeks, and in some cases, even months. And sometimes they also add custom obfuscation into malware. Custom obfuscation is obfuscation that cannot be broken through publicly available tools. And I personally met the situation in March 2022 when I needed to analyze a .NET wiper called 00 that was deployed in Ukraine. Its code was extended to tens of thousands lines through a technique that's called control flow flattening. I'll tell you how it works later, but for now, I'll say that it is considered to be one of the most tough to crack techniques. Of course, this technique is not new, and it has been previously researched for C and C++ malware. And there is even a plugin for IDA that allows you to remove flattening from C and C++ code. However, in my case, I was dealing with C#. Although C, C++, and C#, these two languages, they sound similar, but C# is entirely different in terms of architecture from C and C++. And existing tools, they didn't work for me. That is why I decided to create my own control flow unflattener for the 00 wiper and fill the gap in the knowledge about unflattening.net. And today, I would like to tell you how you can create your own unflattener for 00. But before we go into deep into the implementation details, let's first discuss overall strategy of how we're going to do it. And to do that, let's first look into 00's code in the NSpy, which is a .NET decompiler. So here we have one of a function. Let's just scroll down it. As we can see, the code is full of junk, and it is unreadable. By the way, as you can see here, this function has 317 lines. Originally, this function consisted of 4 lines. And although we see junk everywhere, it looks as if code has been made in hell. We can see a pattern in this junk. And let's look at this pattern attentively. Over here, we have an array of integers being assigned. And if we look at some of these integers, we will notice that they look quite large and random. Like here, look, 2 billion, 1 billion, those integers seem random. And we have 5 such integer arrays right here. And now let's look at what we do with those integers. We iterate over the arrays of integers in a while loop. And we pass every array to this function with a random name. Let's try to deduce what this function does. To do that, let's look at the return value. It's an integer called num. And this integer, as we can see, is being compared to 2 values, 19 and 221. These are quite small values, so our function accepts quite big integers as an input and returns small integers as an output. That is why we can deduce that this function is an integer decryption function. And now let's see what we do with the decrypted integer. As I've said, we compare it to a number, 13 or 121. If the number is 13, we take this goto statement right here. And if it's 121, we fall into this large piece of code, and here we have this pattern that we saw earlier. Just by looking at the code with our naked eyes, we cannot deduce which if gets executed first, the one with 13 or the one with 121. However, the program knows how to execute these if conditions in a correct deterministic order because it has access to the execution order array. But we, reverse engineers, when we look at it, we can see it. And so, this technique that involves rearranging lines of code in a random order and then using an execution order array, this technique is called control flow flattening. And now let's try to remove it. But again, before we dig deep into implementation details, we first have to mark the overall strategy of how we're going to do it. This way, it will be way more easier to code stuff. So as we remember, we are dealing with an execution order array of integers. We need to extract this array. After we do that, we need to match every number in the execution order array to lines of code that correspond to it. Let me show you an example. In the case of num equals 13, we execute this line, a goto statement. We have to mark this line as corresponding to number 13, as well as everything that is at that goto statement, namely these lines of code. So we have to mark all the lines which are executed with a particular execution order number. And once we do that, we have to rearrange code, just move blocks of code, and this way we'll get an unflattened binary, restore the original function. And now, let's go over each of these steps in greater detail. Now, about the execution order, we all remember that it is stored in an array, and this array has a type array of objects. And this array of objects includes arrays of integers. And in order to detect execution order arrays in our code, we can use those two data types as a pattern. And as we will see later, this pattern is efficient enough. It detects all the execution order arrays, and it does not give any false positives. Now, that's pretty much it for the first step, and now the second step, extracting lines that match a certain execution order number. We can propose the following strategy. It's kind of obvious, like here, we can take the whole binary and decompile it into C#. We'll have files of code with functions, and then we'll iterate over every function, and we'll find if statements which compare the execution order variable. And then here we have curly braces. We take the code between curly braces right here, and this is our code. But unfortunately, this approach, it has a problem. And this problem, as you may see, maybe, it's goto statements. Here, take a look at num equals 13, and take a look at this goto statement. This goto statement, it leads to code, this code again. Now, this code is outside the curly braces, which correspond to the num equals 13 if statement. There is the brackets end there, and the code that we need is elsewhere. That is why, if we use a strategy of just working with text, we may lose some important code. So we need something smarter, and we can arrive at a smarter solution if we treat code not as a file with text of lines with lines, but as a graph. On the screen, you see a graph that consists of blocks of code. And these blocks of code are connected with arrows. Whenever there is a branch in the code, we connect the two blocks with an arrow. And if you look attentive enough, you will notice that we have three types of arrows here. We have an orange arrow. An orange arrow, we draw it if the two blocks are connected through an unconditional jump. Then we have the red arrow. A red arrow means a false branch of an if statement, and a green arrow means a true branch of an if statement. And these blocks of a graph, they are called basic blocks. And this whole graph is called a control flow graph. And now let's see how we can leverage control flow graphs to match execution order numbers to blocks of code. Here you can see we have some blocks that have bold text. we need to assign an execution order number to each of these blocks. These are useful blocks that were present in the original binary. We need them. And now let's see how we can do it. I'll demonstrate. We will start traversing the graph from the very top, and we'll do that. We'll explore all possible paths in our graph until we hit an if statement with an execution order variable. Let me show you that to you. We're currently located in the top node, and then we follow the orange arrow and we go down into the while loop. Here you can see we have two arrows, two branches. The red branch leads to a return statement. This is a dead end. We go to another branch, which is, in our case, an if condition. This is the if condition that we need. It compares the execution order variable. Whenever we see such an if condition, we enter marking mode. Let me explain what marking mode is. We go to the true branch of the if condition, and we again explore all possible branches that we see. But the difference is that if we see a new block, we mark it as corresponding to an execution order number. Again, let me demonstrate that. We go to the true branch, and we hit block 1 of number equals 121, and we assign it a color. A color means an execution order number, and blue color in our case means 121. Then we have two branches here. Let's go first to the true branch of the if statement. By doing that, we arrive at block 3. It is a new block, we mark it, we assign it a color. From here, we follow the orange arrow, and we arrive at the I++ block. Now, this block, what it does is that it only increments the index used for the execution order array. It does not correspond to any of the execution order numbers. You can notice that it can be reached from num equals 13 of the graph. That is why, when we reach this block, we consider this branch a dead end, and we go to another branch, which we'll do. And this new branch will be the false condition of the if statement, the red arrow of block 1. By following it, we go to block 2. Again, assign it an execution order number. Blue is 121. Now, we go to the orange arrow, and again we arrive at I++. Again, a dead end. Now we have finished exploring the num equals 121 branch, but we have another if condition here, num equals 13. Let's again follow the steps that we've done before. We go to the true branch, encounter a block, and mark it. Now the color is green. Green means 13. Then we go to the orange arrow, again I++, again a dead end. And as you can see here, we have successfully assigned a color and execution order number to each of the blocks with bold text. And this is it for matching lines of code. And now we have to perform reordering. Let me show you what I mean by reordering. Let's say we have to execute the green block after the blue block. We first execute 121 and then 13. In order to connect the blocks in the correct order, we have to attach the blue block number 2 to the green block number 1, and the blue block number 3 to the green block number 1. And if we do that, we'll obtain something like this. And this is the control flow graph for the unobfuscated function. Now, all we have to do is convert this graph to C# code, and we'll obtain the unflattened function. So that's it for the strategy, and now let's see how we can automate the unflattening, how we can code the unflattener. To do that, we'll use deofdot. It's a command line utility. It's a popular command line utility used for deobfuscating .NET binaries. And you may have heard of deofdot when you were performing .NET malware analysis. You may have used it for unpacking .NET malware or for performing string decryption in .NET. So this tool, it already implements deobfuscators for popular .NET protectors such as .NET Reactor. But today, we're not going to just launch deofdot. Instead, we're going to modify its code and add our own deobfuscator to it. And as we will see, working with deofdot turns out to be very comfortable. In order to start working with dfo.dot, you have to head to its official repository and download the source code. Then you open it in Visual Studio. After that, you head to the dfo.dot code project and open a folder called deobfuscators. And this folder, it contains many subfolders. Each of these folders corresponds to a different deobfuscator. We'll create our own folder in it and create our own deobfuscator. We'll name our folder 00. Then we have to place a template file for our deobfuscator. What's important to know about this template file is that we have to assign a name for our deobfuscator, which will be 00 in our case. And once we assign the name, we can compile dfo.dot and launch it through the command line. And if we have done everything correctly, we will see the description of our deobfuscator appear among the list of all deobfuscators. So right now, our deobfuscator does nothing. It's just a template. And let's add useful features to it. As we remember, our strategy heavily relies on constructing control flow graphs of functions. dfo.dot allows you to do that by defining a class that's called a block deobfuscator. We should define this class in our code, and it should implement the iBlocks deobfuscator interface. As you can see from the slide, this interface has 3 methods. We are interested only in the last one, which is called deobfuscate. Now, if we define this method, then dfo.dot will iterate over every function in the obfuscated binary. It will construct a control flow graph for every function. And for every function, it will call the deobfuscate method of our block deobfuscator. It will pass the constructed control flow graph as a list of blocks in the all blocks argument. And then we'll iterate over this list of blocks. While iterating, we'll be looking for execution order arrays. We have earlier agreed to detect those execution order arrays with data types, the array of objects and the array of integers. But before we do any pattern matching, before we code any pattern matching, we need to first know that in dfo.dot, control flow graphs, unlike we saw earlier, they do not contain C# code. Instead, they contain a special kind of assembly called intermediate language. It's a special assembly for .NET binaries. And we can compare the C# code with assembly in the NSPI if we here select intermediate language. So this is how this assembly looks like. And if we compare the C# code and the assembly for assigning something to an array of objects, we will see that it contains 2 instructions. We are interested in the second instruction, which is called newR. We can use this instruction to perform pattern matching, and let me show you how you can do that in C#. We first check that the opcode of the instruction, the name of the instruction, is called newR. And then we check that the operand, the parameter of this instruction, is system.object. Now, if this pattern works, then we are probably dealing with an execution order array. And what we need to do next is to extract numbers from it. Now, if we again go to the NSPI and compare the C# code with intermediate language, we will notice that an assignment of an integer array with a constant value gets compiled to 3 instructions. We are interested only in the first instruction, which is called LD token. It's important to us because this the operand, the parameter of this instruction, it contains a so-called token. A token is a reference to the array value. In order to extract a value from the token in C# with dfo.dot, we have to take the instruction's operand and then take its initial value method. By doing that, we'll obtain an array of bytes. But we don't need an array of bytes. We need an array of integers. In order to convert an array of bytes to an array of integers, we need to group every 4 integers. Every 4 bytes, we group every 4 bytes into an integer, and the order of bytes is little endian. And then, once we do that for every array, we will pass every array to the decryption function, and by doing that, will obtain an array of integers with the execution order. Like in our case, the array would consist of two values, 13 and 121. Now, what we also did at the second step is that we traversed the control flow graph. But we didn't just explore all the basic blocks in a random order. We followed the arrows. We can't just iterate over the blocks in a for loop. We need to iterate over the blocks through arrows. And d4.dot also allows you to do that. A block object in d4.dot, it has two fields. The first field is called fall-through. A fall-through field corresponds to either an orange arrow, an unconditional jump, or a red arrow, which is a false branch of an if statement. You can see an example on the graph at the screen. And another member is called targets. It's an array. It may correspond to a green arrow, a true branch of an if statement, or it may correspond to a switch statement. By exploring the graph through those fall-through and targets fields, we will be able to follow the arrows and traverse the graph in the order that we need and visit every basic block. And now the last step, reconnecting blocks. Surprisingly, in d4.dot, you can perform reconnection of basic blocks in just one line of code. Imagine if you had to perform basic block reconnection in a disassembler such as IDA or Ghidra. In this case, you would probably have to write a script, like an IDA Python script, consisting of at least maybe 100 lines. But with d4.dot, it's just one line of code. If you want the two blocks to be connected through an unconditional jump, then we use the setNewFallthrough method. An unconditional jump, it may correspond to either a orange or a red arrow. But if we want the blocks to be connected through a true branch of an if statement, then we use the setNewTarget method. In all cases, the new target block is specified in the method arguments. And once we do that, we have to piece those three steps in a single program, in a single deobfuscator, and then we'll be able to launch d4.dot, and it will deobfuscate the binary. If you are interested in low-level details, I suggest you to look at my code of the deobfuscator on GitHub. And as for the strategy that we use today, it can be applied to any programming language. It's independent of a programming language. All you need to do is a way to extract execution order numbers, the execution order sequence. Then you have to match every number in the sequence to lines of code, and then to reconnect those lines of code. And as for d4.dot, as for .NET, it turned out to be extremely convenient to perform all those three steps using d4.dot. And that is because d4.dot allows you to perform complex things like reconnecting blocks, as we saw, in a rather small number of code, one line in our case. When I was coding the deobfuscator, I expected it to be at least a few thousand lines long. But much to my surprise, it turned out to be only 250 lines of code. For a complex obfuscation such as control flow flattening, I believe that it's amazing. Maybe the code of the obfuscator that the malware developers used, maybe it had more lines than the obfuscator. I hope that today I helped you learn something new about control flow unflattening or d4.dot. I advise you to go to the GitHub repository with the unflattener and take a look at it. The code is very small, 250 lines, and I put comments into it. I put a lot of comments into it. I tried to make it as readable as possible. I especially advise you to do that if you ever tried to understand how to perform control flow unflattening. Maybe if you tried to search for some articles, but for some reason you couldn't figure it out. In this case, please download the code, load it into Visual Studio, and debug it step by step. Explore the variables, their values, and once you spend some time debugging the code and running it step by step, I'm sure that you will understand how to perform control flow unflattening. And right now, if you have any questions, I'm ready to answer them. Thank you.
Thank you, Georgy, for the interesting presentation. We have plenty of time for questions. One is at the back.
Hey man, firstly, that was awesome. I know you're a second-year student at university. Like your trajectory is insane. So congrats, that was awesome. The control flow flattening technique, is that something that's implemented by a number of threat actors that you've seen, or is it specific to 00 on its own?
Thank you very much for your question. I met control flow flattening in many malware families. First of all, common malware families like Emotet, it's there. Then it's also implemented in complex malware like Finfisher. It was a malware, a commercial spyware, an APT. It also had control flow flattening in C and C++. So it is quite widespread. But although it is widespread, every malware developer implements control flow flattening in their own way, and that is why there is no silver bullet to countering it. In every case, you have to find pattern matching stuff, and for every malware, you have to tune the deobfuscator. Any more questions?
I have one question if there are no more questions. So you say you practically have to write a new deobfuscator for each family. How much time does it take, in your estimation?
It depends on the level. If you are experienced with writing the obfuscators, if you ever wrote one Unflattener, then it will maybe take just maybe from few hours to 1 day to tune whatever you have. It depends on the complexity and the language. For me, I had no prior experience of writing from scratch the obfuscator. So on Flatteners, I didn't have any experience. So I spent like about 3 days, like looking through different code and then exploring the possibilities. It took me 3 days. And in the case of 00, maybe you analyzed it. It's a small wiper. And if you are out of time, it may be actually better to just run the code in a debugger. But it's important to know how to perform such things, because if you have a sophisticated framework consisting of tens of modules, then just running everything in a debugger won't work. And you have to resort to static analysis. So it depends on the complexity and whatever level of knowledge you have.
Thank you again for a very interesting presentation.
Welcome.
It was very useful.